Every particle of matter you have ever encountered has a twin, an antimatter counterpart that is its exact opposite. The electron has the positron, the proton has the antiproton. When they meet, they annihilate each other in a flash of pure energy. This is one of the most fundamental symmetries in all of physics, but there is one particle that might break this rule entirely: the neutrino. Because the neutrino carries no electric charge, it is possible that the neutrino and its supposed antimatter twin are not two different particles at all, but the same particle. Not similar, not related, identical. If this is true, it would mean a neutrino is its own antiparticle, something no other known matter particle does. The consequences would reshape our understanding of mass, symmetry, and why the universe is made of matter instead of nothing. No experiment has settled this. The answer remains unknown. If you find this kind of deep exploration into the unsolved mysteries of physics interesting, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. To understand why this question matters, and why it is so difficult to answer, we need to start with one of the most profound discoveries in the history of physics: the discovery of antimatter. Every piece of matter you have ever touched, every atom in your body, every molecule of air you have ever breathed, all of it is built from a small number of fundamental particles. Electrons orbit nuclei. Protons and neutrons sit packed together inside those nuclei. And deeper still, quarks make up the protons and neutrons themselves. These are the building blocks of everything you see around you: the chair you are sitting in, the screen you are looking at, your own hands. All of it, the same handful of particle types arranged in different configurations. But in the late 1920s, physics revealed something no one had expected. Every single one of these particles has a mirror image, a counterpart that is identical in almost every way. Same mass, same spin, same fundamental structure, but with the opposite electric charge. An electron carries negative charge. Its mirror image, called the positron, carries positive charge. A proton carries positive charge. Its mirror image, the antiproton, carries negative charge. These mirror image particles are called antiparticles, and together they make up what we call antimatter. This was not a discovery anyone went looking for. No experiment hinted at it. No observation suggested it. Antimatter was revealed by pure mathematics, and the story of how that happened is one of the most remarkable episodes in the entire history of science. In 1928, a British physicist named Paul Dirac was working on what seemed like a technical problem. He wanted to write a single equation that could describe the behavior of the electron in a way that was consistent with both quantum mechanics and Einstein's special relativity. Both theories had been confirmed by experiments. Both worked extraordinarily well in their own domains. Quantum mechanics governed the behavior of atoms and subatomic particles. Special relativity governed objects moving at or near the speed of light. But combining them into a single mathematical framework for the electron had proven stubbornly difficult. The existing equations either satisfied quantum mechanics but not relativity, or satisfied relativity but not quantum mechanics. Nobody had managed to make both work at the same time. Dirac succeeded. He wrote an equation, now called the Dirac equation, that described the electron in a way that satisfied both frameworks simultaneously. It was a triumph of theoretical physics, an equation of breathtaking elegance. But there was a problem. The equation had two sets of solutions. One set described the electron exactly as expected, a negatively charged particle with a certain mass and a specific type of spin. Everything matched beautifully. The other set described something that no one had ever seen. It described a particle with the same mass as the electron, the same spin, but with the opposite charge, positive instead of negative. At first, Dirac was not sure what to make of this. He considered the possibility that the second solution was just a mathematical artifact, something that appeared in the equations but did not correspond to anything real in nature. Maybe the equation was more general than the physical world it described. Maybe only one solution had physical meaning and the other could be safely ignored. But ignoring it was not so easy. The mathematics was clear and unyielding. The structure of the equation did not allow you to simply throw away one set of solutions without breaking the entire framework. Both solutions were consequences of the same equation. You could not keep one and discard the other. If the equation correctly described the electron, and it did with extraordinary precision, then the mirror image particle had to be just as real. The math demanded its existence the way arithmetic demands that 2 + 2 = 4. You cannot accept the equation and reject its consequences. Dirac himself gradually came to accept this conclusion. In 1931, he published a paper predicting the existence of what he called the anti-electron, a positively charged particle with the same mass as the electron. This was a bold prediction. Physics had never suggested anything like this before. There was no experimental evidence for such a particle. Nobody had ever observed a positively charged electron in any laboratory, in any cosmic ray detector, in any observation of any kind. But the mathematics demanded it, and Dirac trusted the mathematics. 1 year later, in 1932, an American physicist named Carl Anderson found it. Anderson was studying cosmic rays, the high-energy particles that constantly rain down on Earth from deep space. He was using a device called a cloud chamber, which makes the paths of charged particles visible as thin trails of condensed vapor. When a charged particle moves through a magnetic field inside the chamber, its path curves. The direction of the curve tells you the sign of the charge, positive or negative, and the tightness of the curve tells you the particle's mass. A heavier particle curves more gently, a lighter particle curves more tightly. Anderson observed a trail that curved the wrong way. It curved like a positively charged particle, bending in the direction that positive charges bend. But the curve was far too tight to belong to a proton, the only positively charged particle known at the time. A proton, being nearly 2,000 times heavier than an electron, would leave a much wider, more gently curving trail. The particle Anderson saw curved like something with the mass of an electron, but with positive charge. It was exactly what Dirac's equation had predicted. Anderson named it the positron. The discovery was extraordinary. Physics had predicted the existence of an entirely new kind of matter, using nothing but mathematics, and nature confirmed it perfectly. Dirac received the Nobel Prize in 1933. Anderson received the Nobel Prize in 1936, and the world of physics had its first glimpse of a pattern that would turn out to be universal. Over the following decades, as physicists built more powerful particle accelerators and developed more sensitive detectors, they found that the positron was not a special case. It was not a quirk unique to the electron. Every matter particle they discovered had a corresponding antiparticle. The proton has the antiproton, discovered in 1955 at the Bevatron accelerator in Berkeley, California. The neutron has the antineutron, detected in 1956. Every type of quark has a corresponding antiquark. Every charged lepton, the electron, the muon, and the tau, each has an antiparticle carrying the opposite charge. No exceptions had ever been found among the charged particles. The pattern was absolute and universal. And this was not just a coincidence or an empirical regularity that might someday be broken. It was built into the deepest mathematical structure of quantum field theory, the theoretical framework that underpins all of modern particle physics. The very equations that describe how particles behave demand the existence of antiparticles. You cannot have one without the other. The existence of antiparticles is as fundamental as the existence of the particles themselves. And when a particle meets its antiparticle, something dramatic and violent happens. They annihilate each other. Both particles disappear entirely, and their combined mass is converted into pure energy, typically in the form of high-energy photons called gamma rays. This process is described by Einstein's relationship E equals mc squared, which tells us that mass and energy are two forms of the same underlying quantity. When an electron and a positron collide, their mass does not simply vanish into nothingness, it transforms into energy. And the reverse can happen too. If you concentrate enough energy into a small enough region, you can create a particle-antiparticle pair from pure energy. Matter and antimatter are constantly being created and destroyed through these processes, especially in high-energy environments like particle accelerators, the cores of stars, and the violent events that shaped the early universe. This symmetry between matter and antimatter is one of the deepest and most robust patterns in all of physics. For every type of matter particle, there is an antimatter twin. The twin shares the same mass, the same lifetime, the same spin. The only difference is that certain intrinsic properties are reversed. And the most visible of these reversed properties, the one that jumps out most clearly, is electric charge. Think about it carefully. If you had an electron and a positron sitting side by side, and you could somehow examine all their properties one by one, the thing that would immediately and unambiguously tell them apart is their charge. The electron is negative. The positron is positive. That is the label. That is the tag. That is the fingerprint. Charge is what makes a particle distinguishable from its antiparticle. It is the identifier that nature uses to keep track of which is which. And this principle extends beyond just electric charge. Particles carry other types of charge as well. Quarks carry something called color charge, which is the charge associated with the strong nuclear force that binds quarks together inside protons and neutrons. Quarks have color charge. Antiquarks have the corresponding anti-color charge. There are also conserved quantum numbers like baryon number and lepton number that are reversed between particles and antiparticles. A proton carries baryon number +1. An antiproton carries baryon number -1. All of these charges and quantum numbers serve the same fundamental purpose. They are labels that distinguish matter from antimatter. They mark the difference. They keep the categories clean and separate. But here is the crucial point, and it is the point on which this entire story turns. All of these labels work because the particles carry them. An electron carries electric charge. A quark carries color charge. These charges give the particles their identity, their individuality, their distinctness from their antimatter counterparts. If you remove the charge, you remove the label. And if you remove the label, you can no longer tell the particle from its antiparticle. The very concept of a distinction between the two begins to dissolve. Now imagine a particle that carries no electric charge at all, no color charge, no interaction with the strong force. A particle so neutral, so thoroughly stripped of the identifying marks that separate matter from antimatter, that there is nothing obvious left to distinguish it from its own mirror image. That particle exists, and it is the neutrino. The neutrino is one of the most abundant particles in the universe. Roughly 65 billion of them pass through every square centimetre of your body every single second, most of them streaming from nuclear fusion reactions deep in the core of the Sun. They are produced in enormous quantities by stars, by radioactive decay, by nuclear reactors, and by cosmic ray interactions in the upper atmosphere. They were produced in staggering numbers during the first seconds after the Big Bang, and a diffuse background of those ancient neutrinos still fills all of space today. The universe is absolutely flooded with neutrinos, and yet, despite being everywhere, they are among the most elusive particles ever discovered. Neutrinos interact with other matter almost exclusively through the weak nuclear force, one of the four fundamental forces of nature, and by far the feeblest at the energy scales relevant to particle interactions. They carry no electric charge, so they are completely invisible to the electromagnetic force. They carry no color charge, so the strong nuclear force ignores them entirely. And while gravity acts on everything with mass, including neutrinos, their masses are so extraordinarily tiny that gravitational effects are negligible under any practical circumstances. The result is a particle that barely notices the rest of the universe. A neutrino can pass through the entire Earth, all 12,700 kilometers of rock, iron, and magma, without interacting with a single atom. It can pass through a wall of lead a light year thick and come out the other side as though nothing was there at all. This extreme reluctance to interact is what made neutrinos so incredibly difficult to detect, and what delayed their experimental confirmation for over 2 decades. The neutrino was first proposed in 1930, when the Austrian physicist Wolfgang Pauli suggested that an unseen neutral particle must be carrying away the missing energy observed in a type of radioactive decay called beta decay. In beta decay, a neutron inside an atomic nucleus transforms into a proton, emitting an electron in the process. But careful measurements had shown that the emitted electron did not carry away all the energy that should have been released. Energy appeared to be vanishing. Either the law of conservation of energy was wrong, which would have been catastrophic for all of physics, or something invisible was escaping the experiment, carrying the missing energy with it. Pauli reluctantly proposed the latter. An unknown neutral particle, too elusive to detect, was slipping away with the unaccounted energy. He called it a desperate remedy. He was not confident such a particle could ever be found, but the math demanded it, just as Dirac's math had demanded the positron. The Italian physicist Enrico Fermi gave the new particle its name, neutrino, Italian for the little neutral one. The detection finally came in 1956, when the American physicists Clyde Cowan and Frederick Rines succeeded in observing neutrinos directly, using a nuclear reactor as an intense source and enormous tanks of specially prepared liquid as a target. Their experiment confirmed that neutrinos were real. The method was ingenious. Cowan and Rines placed their detector right next to a nuclear reactor, which produced an enormous flood of antineutrinos. When an antineutrino struck a proton in their specially prepared liquid, it produced a positron and a neutron through a process called inverse beta decay. The positron immediately annihilated with a nearby electron, producing a pair of gamma rays. A fraction of a second later, the neutron was captured by cadmium atoms dissolved in the liquid, producing a second burst of gamma rays. This distinctive double flash, 2 pulses of light separated by a precise and predictable delay, was the unmistakable signature of a neutrino interaction. No known background process could convincingly fake that pattern. They interacted so rarely that you needed a tremendously intense source and a very large detector to catch even a handful. But they were undeniably real. Now, here is where the story takes its critical turn. When physicists study antimatter, they are accustomed to a clear and unambiguous distinction between particles and antiparticles. The electron is not the positron. The proton is not the antiproton. You can always tell them apart by measuring their charge. This distinction is not just a matter of convenient labeling, it has physical consequences. An electron and a positron annihilate each other precisely because they are different particles with opposite charges. If they were the same particle, the concept of mutual annihilation in this way would not apply. For every charged particle, the distinction between matter and antimatter is absolute, immediate, and unmistakable. You simply measure the charge. Positive or negative, particle or antiparticle. There is never any ambiguity. But the neutrino is neutral. It has 0 electric charge, and this simple fact changes everything. When the Dirac equation predicts an antiparticle, it predicts a particle with the opposite charge. For the electron, you get the positron. Negative becomes positive. The distinction is sharp and permanent. But what is the opposite of zero? It is zero. The opposite of no charge is no charge. If the defining feature that separates a particle from its antiparticle is the reversal of charge, and the charge happens to be zero, then what exactly is it that distinguishes the neutrino from the antineutrino? This is not just a clever philosophical puzzle. It is a question with real, measurable physical consequences, and it leads to two very different possibilities for what the neutrino fundamentally is. The first possibility is that neutrinos and antineutrinos really are distinct particles, even though they share the same electric charge of zero. In this scenario, they are distinguished not by electric charge, but by another quantum number called lepton number. Physicists assign lepton number to particles in the same way they assign electric charge. The electron carries a lepton number of +1, so does the neutrino. Their antiparticles, the positron and the antineutrino, each carry a lepton number of -1. In every particle interaction ever observed, the total lepton number before and after the reaction remains exactly the same. It is conserved. If lepton number is a genuine, fundamental, unbreakable symmetry of nature, then the neutrino and the antineutrino are truly different particles. They carry different values of a conserved quantity. They are as distinct as the electron and the positron, just distinguished by a harder-to-measure form of charge. The second possibility is more radical. It is possible that lepton number is not a truly fundamental symmetry at all, that it is only approximately conserved, or even that it is not conserved in certain extreme circumstances. If that is the case, then there would be nothing left, no charge, no quantum number, no hidden label of any kind that truly separates the neutrino from the antineutrino. They would be the same particle, a single entity that sometimes behaves as what we call a neutrino, and sometimes behaves as what we call an antineutrino, depending only on the circumstances of its interaction. Now, you might be wondering how physicists currently tell neutrinos from antineutrinos apart, if the question of whether they are truly different has not yet been settled. The answer reveals just how subtle this entire situation is.
In practice, physicists distinguish them by the way they interact. When an electron neutrino collides with a neutron through the weak force, it produces a proton and an electron. When an electron antineutrino collides with a proton, it produces a neutron and a positron. The final products are different. An electron in one case, a positron in the other. And this difference is consistent, reliable, and has been confirmed in every experiment ever conducted. In practice, you always know which one you are dealing with by looking at what it produces. But here is the subtle part. This distinction might not prove that neutrinos and antineutrinos are fundamentally different particles. It might simply reflect a difference in their spin orientation relative to their direction of motion, a property physicists call handedness or helicity. All observed neutrinos are left-handed. This means that if you could watch a neutrino flying toward you, it would be spinning counterclockwise relative to its direction of travel. All observed antineutrinos are right-handed, spinning clockwise relative to their direction of travel. This difference in handedness is what determines how they interact with other particles through the weak force. The weak force is inherently asymmetric in a way that no other force is. It couples only to left-handed particles and right-handed antiparticles. This was a shocking discovery when it was first confirmed in the late 1950s, and it remains one of the most striking features of the weak interaction. So when we say we have detected a neutrino versus an antineutrino, what we have actually detected is a left-handed neutral particle producing an electron versus a right-handed neutral particle producing a positron. We call one a neutrino and the other an antineutrino. But are they truly different particles? Or are they the same particle seen in two different spin states?
For a charged particle like the electron, this question does not arise. Even if you could flip an electron's spin to the opposite orientation, it would still be an electron. It would still carry negative charge. Charge is an intrinsic property that does not depend on how the particle is spinning or how it is moving. But for a neutral particle like the neutrino, there is no charge to anchor the distinction. If a left-handed neutrino and a right-handed antineutrino are really the same particle, just spinning in different directions relative to its motion, then the neutrino is its own antiparticle. And the entire matter-antimatter distinction for neutrinos would be something we invented, not something nature enforces. There is one more piece of this puzzle, and it is the piece that makes the question genuinely urgent rather than merely interesting. For a long time, physicists believed that neutrinos might have exactly zero mass. If neutrinos were truly massless, they would always travel at the speed of light, and their handedness would be an absolute, unchangeable property. A left-handed neutrino would be left-handed forever, no matter who observed it or how they were moving. You could never flip its handedness, because to do so, you would need to overtake it and observe it from the other side. And you cannot overtake something that travels at the speed of light. In a massless world, the distinction between neutrinos and antineutrinos could be maintained entirely by handedness, even without electric charge. But beginning in the late 1990s and continuing into the early 2000s, a series of groundbreaking experiments demonstrated that neutrinos do have mass. The masses are incredibly small, at least 1 million times lighter than the electron, which is itself the lightest known charged particle. But they are not zero. This was a historic discovery, one that earned a Nobel Prize and rewrote textbooks, and it changed the entire landscape of the neutrino identity question. If a neutrino has mass, it does not travel at the speed of light.
It travels slightly slower, and this means that you could, at least in principle, travel faster than the neutrino and look at it from the other direction. From that new vantage point, a left-handed neutrino would appear to be right-handed. The handedness that seemed to mark it as a neutrino rather than an antineutrino is no longer an absolute property of the particle. It has become a matter of perspective, something that depends on the relative motion of the observer. This is why the discovery of neutrino mass made the question of the neutrino's identity so much more pressing. When neutrinos were thought to be massless, you could maintain the distinction between neutrino and antineutrino through their permanent, fixed handedness. The two states were forever separate, but mass connects them. Mass allows the handedness to change with perspective, and if the two states that we call neutrino and antineutrino are connected in this way, then the possibility that they are actually the same particle becomes very difficult to dismiss. This is the heart of the mystery. The neutrino is the only known matter particle that is electrically neutral. It is the only one where the usual labels that separate matter from antimatter fall silent. It is the only one where the question of whether it is its own antiparticle remains genuinely, stubbornly open. For every other matter particle, the answer is clear and definitive. The electron is not the positron. The up quark is not the anti-up quark. The muon is not the anti-muon. Electric charge settles the question instantly and without any room for doubt. But for the neutrino, charge offers no help. The neutrino has zero charge. The antineutrino has zero charge. The one property that reliably and permanently separates matter from antimatter for every other particle in the known universe is exactly the property that the neutrino does not possess. And so physics is left with a question it cannot yet answer. Is the neutrino a particle with a genuinely distinct antiparticle, kept separate by a conserved quantity called lepton number, existing as two truly different entities despite sharing the same charge? Or is the neutrino its own antiparticle, a single particle whose apparent double identity
is merely a consequence of its spin and the peculiarities of the weak force. The first possibility is called a Dirac neutrino, named after Paul Dirac, whose equation describes particles with distinct antiparticles. The second possibility is called a Majorana neutrino, named after the Italian physicist Ettore Majorana, who showed in 1937 that a neutral particle could serve as its own antiparticle without any mathematical contradiction whatsoever. Both possibilities are fully consistent with everything we have observed so far. Every neutrino experiment ever performed, every measurement of neutrino interactions, every detection of neutrino oscillations, all of it can be explained equally well by either interpretation. The data does not yet distinguish between the two. This is not because we have not tried. It is because the difference between a Dirac neutrino and a Majorana neutrino reveals itself only in extremely rare processes that push the absolute boundaries of our experimental capabilities. The experiments needed to tell the difference are among the most sensitive and technically demanding ever attempted in the history of science. And what hangs in the balance is not just a classification, not just a label for the neutrino in the catalogue of known particles. What hangs in the balance is our understanding of some of the deepest questions in physics: the origin of mass, the fundamental symmetries that govern the behavior of matter, and perhaps most profoundly, the question of why the universe is made of matter at all, why there is something rather than nothing. Because if the neutrino is its own antiparticle, then a symmetry of nature that we have always assumed to be exact, a rule called lepton number conservation, is broken. And if lepton number can be violated, it opens the door to processes that could explain one of the greatest mysteries in all of science: the fact that our universe contains overwhelmingly more matter than antimatter, even though the Big Bang should have produced them in precisely equal amounts. The neutrino is the quietest particle in the universe, the most ghostly, the most elusive, the most reluctant to interact with anything around it. It passes through planets without stopping. It barely acknowledges that the rest of the universe exists. And yet this ghost of a particle, this little neutral one, may carry within its identity the answer to why anything exists at all. Why there are stars and galaxies and planets and people, rather than a universe of pure radiation and empty space. That answer has eluded physics for decades, and the search for it is being conducted right now, in laboratories buried deep underground, shielded from cosmic rays by thousands of feet of solid rock, where the most sensitive detectors ever built wait patiently in silence for a signal so faint it may never come, or that may finally settle the deepest question about the neutrino once and for all. In 1937, just 9 years after Dirac published the equation that predicted antimatter, a young Italian physicist named Ettore Majorana put forward an idea so radical that the physics community largely ignored it for decades. Majorana was, by all accounts, a genius of extraordinary depth. Enrico Fermi, himself one of the greatest physicists of the 20th century, once compared Majorana's talent to that of Galileo and Newton. This was not a casual compliment. Fermi was careful with praise and not given to exaggeration. He recognized in Majorana something rare, a mind that could look at a familiar problem and see possibilities no one else had imagined. Majorana's insight began with the same equation that had given physics the positron, the Dirac equation. As we have seen, this equation describes particles that have distinct antiparticles. The electron gets the positron, the quark gets the antiquark. Each matter particle has a mirror twin with opposite charge. This structure is built into the mathematics of the equation itself, and for charged particles it is inescapable. If a particle carries electric charge, the Dirac equation demands that it have a separate antiparticle carrying the opposite charge. There is no way around this. The mathematics does not allow a charged particle to be its own antiparticle. But Majorana noticed something that others had overlooked. When the particle in question carries zero electric charge, the mathematics changes in a subtle but profound way. The Dirac equation still works. It still produces solutions. But it is no longer the only option. For a neutral particle, there is a different equation that works just as well. An equation in which the particle and its antiparticle are not two separate entities, but one and the same. The particle is its own antiparticle. It does not have a mirror twin because it is its own mirror twin. Majorana wrote this equation down, proved that it was mathematically consistent, and published it in a paper in 1937. Then, 1 year later, in 1938, Majorana vanished. He boarded a ship from Naples to Palermo and was never seen again. No body was ever found. No conclusive explanation has ever been established. Some believe he took his own life. Others believe he chose to disappear and live in obscurity. Decades of investigation have never settled the matter. It is one of the strangest and most tragic stories in the history of science. The physicist who proposed that a particle might have a hidden double identity became himself a figure shrouded in mystery and ambiguity. But Majorana's equation survived, and the question it raised has only grown more important with time. To understand why, we need to look very carefully at what makes a Dirac neutrino different from a Majorana neutrino. Not just in abstract theoretical terms, but in terms of what each possibility actually means for how the universe works. Let us start with the Dirac option, because it is the more familiar one. It follows the same pattern as every other matter particle we know. In the Dirac picture, the neutrino and the antineutrino are genuinely different particles. They are as distinct from each other as the electron is from the positron. The fact that they share the same electric charge of 0 does not make them identical, any more than two people with the same height are the same person. There are other properties that distinguish them. The property that does the distinguishing, in the Dirac picture, is lepton number. This is a bookkeeping quantity that physicists assign to particles involved in weak interactions. The neutrino carries lepton number +1. The antineutrino carries lepton number -1. In every interaction ever observed, the total lepton number before the reaction is exactly equal to the total lepton number after the reaction. It is conserved. It never changes. When a neutron decays into a proton, an electron, and an antineutrino, the lepton number balances perfectly. Before the decay, the lepton number is 0 because the neutron is not a lepton. After the decay, the electron contributes +1 and the antineutrino contributes -1, giving a total of 0. Everything balances. Everything is consistent. If lepton number is a genuine, fundamental, unbreakable law of nature, then the neutrino and antineutrino are permanently and absolutely distinct. They carry different values of a conserved quantum number. You could never turn one into the other without violating this conservation law. They are two separate particles that happen to share the same electric charge, the same way two different keys might have the same color but open completely different locks. The Dirac picture treats lepton number as a sacred rule. It is the wall that stands between the neutrino and the antineutrino, the barrier that keeps them apart even though charge cannot. Now consider the Majorana option. In this picture, lepton number is not a fundamental law of nature at all. It is an approximation, a pattern that holds in all the interactions we have observed so far, but not a deep truth about the universe. If lepton number can be violated, then the wall between neutrino and antineutrino dissolves. There is nothing left to separate them. No charge, no conserved quantum number, no hidden property of any kind. The neutrino and the antineutrino are one and the same particle. This does not mean that what we call the neutrino and what we call the antineutrino behave identically in experiments. They do not. As established, a neutrino produces an electron when it interacts, while an antineutrino produces a positron. This difference is real and measurable. But in the Majorana picture, this behavioral difference is not because they are different particles. It is because they are the same particle in two different states. Specifically, two different spin states. To understand this properly, we need to go deeper into a concept called chirality, which is related to, but subtly different from the handedness we touched on earlier. In everyday language, handedness and chirality are often used interchangeably, but in particle physics, they refer to two distinct things, and the distinction between them matters enormously for the neutrino identity question. Helicity is a mechanical property. It describes which direction a particle is spinning relative to its direction of motion. If you could watch a particle flying directly toward you, and it appeared to be spinning counterclockwise, physicists would call that left-handed helicity. If it appeared to be spinning clockwise, that would be right-handed helicity. Helicity is intuitive. You can picture it. And for a particle moving at a definite speed, helicity is well defined and measurable. But helicity has a problem. For a particle with mass, helicity depends on the observer. This is a direct consequence of special relativity. If a massive particle is flying to the right and spinning counterclockwise relative to its motion, a left-handed configuration, an observer who is moving even faster to the right could overtake the particle. From that observer's perspective, the particle would now appear to be moving to the left, while still spinning the same direction. The relationship between the spin direction and the motion direction has flipped. What was left-handed is now right-handed. The helicity has changed, not because anything physical happened to the particle, but because the observer changed their frame of reference. For a massless particle traveling at the speed of light, this cannot happen. You cannot overtake something traveling at light speed. So for a massless particle, helicity is absolute. It is the same for all observers. It is a permanent, intrinsic, unchangeable property of the particle. This is why, when neutrinos were thought to be massless, the distinction between neutrinos and antineutrinos seemed perfectly safe. Left-handed helicity was a permanent label. Right-handed helicity was a permanent label. The two could never mix. Chirality is different. It is a more fundamental mathematical property defined by how a particle transforms under the equations of the Standard Model. Chirality is always well defined, regardless of the particle's mass. It does not depend on the observer. It does not change with reference frame. It is an intrinsic property of the quantum field itself, not a mechanical feature of how the particle moves through space. For a massless particle, chirality and helicity are the same thing. A left chiral massless particle always has left-handed helicity, and vice versa. The two concepts are perfectly aligned. But for a massive particle, chirality and helicity can differ. A particle with definite chirality is actually a quantum superposition of both helicities, and a particle with definite helicity is a superposition of both chiralities. Mass mixes them. Mass connects left and right in a way that cannot be undone. This is not just a technical detail, it is the crux of the entire Dirac versus Majorana question. In the Standard Model as currently written, neutrinos come in only one chirality, left chiral. There is no right chiral neutrino in the Standard Model. This was perfectly fine when neutrinos were thought to be massless, because for a massless particle, chirality and helicity are identical, and a purely left chiral, left-handed neutrino could exist without any contradiction. But mass requires both chiralities. This is one of the most important facts in all of particle physics, and it is essential for understanding the neutrino identity problem. Here is why. For every other massive particle in the Standard Model, mass is generated through the Higgs mechanism. A particle interacts with the Higgs field, and this interaction converts left chiral particles into right chiral particles, and vice versa. This constant flipping back and forth between left and right chirality is, in a deep mathematical sense, what mass is. Mass is the coupling between the left chiral and right chiral components of a particle. Without both components, the coupling cannot exist, and the particle cannot have mass. For the electron, this works perfectly. The Standard Model contains both a left chiral electron and a right chiral electron. The Higgs field couples them together, and the electron gets its mass. For quarks, the same thing happens. Left chiral and right chiral components exist for every quark. The Higgs couples them, and quarks acquire mass. But for neutrinos,
the standard model contains only the left chiral component. There is no right chiral neutrino in the standard model. When neutrinos were thought to be massless, this was not a problem. No mass meant no need for a right chiral partner. Everything was consistent. Then came the discovery that neutrinos do have mass. The evidence accumulated across several landmark experiments. In 1998, the Super Kamiokande experiment in Japan, a colossal detector containing 50,000 tons of ultra-pure water buried deep beneath a mountain, reported that muon neutrinos produced by cosmic ray interactions in the atmosphere were disappearing before reaching the detector. They were not simply vanishing, they were transforming into a different type of neutrino, a phenomenon called neutrino oscillation. A muon neutrino would start its journey as a muon neutrino, but by the time it reached the detector, it had converted into a tau neutrino. It had changed its flavour mid-flight. This was astonishing. And the mathematics of neutrino oscillation is unambiguous on one critical point. Neutrino oscillation can only occur if neutrinos have mass. If neutrinos were truly massless, oscillation would be impossible. The fact that oscillation was observed meant, with absolute certainty, that at least some neutrinos have non-zero mass. The result was confirmed and extended by the SNO experiment, the Sudbury Neutrino Observatory in Canada, which demonstrated that electron neutrinos produced in the core of the Sun were oscillating into muon and tau neutrinos during their journey to Earth. This solved a decades-old puzzle known as the solar neutrino problem. The fact that detectors on Earth consistently measured only about 1/3 of the electron neutrinos that solar models predicted. The missing neutrinos were not missing at all. They had simply changed flavour. They were still there, but they had become invisible to detectors designed to see only electron neutrinos. Takaaki Kajita of Super Kamiokande and Arthur MacDonald of SNO shared the Nobel Prize in Physics in 2015 for this discovery. The confirmation that neutrinos have mass was one of the most significant experimental results in particle physics in the past half-century. It was the first clear evidence that the standard model, for all its extraordinary success, is incomplete. The standard model, in its original form, predicted that neutrinos should be exactly massless. Nature disagreed. And this disagreement is what makes the Majorana question so urgent. Because if neutrinos have mass, then something is providing that mass. Some mechanism is coupling the left chiral neutrino to a right chiral partner, generating the mass in the same way the Higgs mechanism generates mass for every other particle. But what is that right chiral partner? Where is it? The standard model does not contain one. There are two options, and they correspond precisely to the two types of neutrino. In the Dirac option, a right chiral neutrino exists. It simply has not been discovered yet, because it does not interact through any of the known forces except gravity, which is far too weak to detect individual particles. A right chiral neutrino would be the most elusive particle imaginable, even more elusive than the ordinary left chiral neutrino. It would carry no electric charge, no color charge, and would not couple to the weak force. It would interact with the rest of the universe only through gravity and through its mass coupling with the left chiral neutrino via the Higgs field. It would be essentially invisible. Some physicists call these hypothetical particles sterile neutrinos, because they are sterile with respect to all the standard model forces. They exist in this picture, but they do not do anything except provide the right chiral partner needed for a conventional Dirac mass. This is a perfectly valid possibility. It works mathematically. It is consistent with all observations. But it has a feature that strikes many physicists as deeply unsatisfying. it does not explain why neutrino masses are so extraordinarily small. Consider how small neutrino masses actually are. The mass of the electron, the lightest charged particle, is about 511,000 electron volts. The masses of neutrinos are not known exactly, but experiments constrain them to be less than half an electron volt. This means neutrinos are at least 1,000,000 times lighter than the lightest charged particle, probably much more. The difference is staggering. In the Dirac picture, there is no natural explanation for this enormous disparity. You simply have to accept that the coupling between the left chiral neutrino and the right chiral neutrino through the Higgs field happens to be extraordinarily, almost absurdly, tiny. The Higgs coupling for the electron is already small. The Higgs coupling for the neutrino would need to be at least 1,000,000 times smaller still. This is not impossible. You can write down a theory where this is true, but it feels arbitrary. It feels like fine-tuning. You are not explaining why neutrino masses are small. You are just declaring them to be small by choosing a very small number and putting it into the theory by hand. This is where the Majorana option offers something remarkable. In the Majorana picture, there is a natural, elegant, almost inevitable explanation for why neutrino masses are so tiny. It is called the seesaw mechanism, and it is one of the most compelling ideas in modern theoretical physics. The seesaw mechanism works like this. Suppose right chiral neutrinos do exist, just as in the Dirac picture. But suppose they are not ordinary right chiral neutrinos with masses comparable to other standard model particles. Suppose instead that they are extremely heavy. Not just a little heavier than other particles, but enormously heavier. Heavier by a factor of trillions. So heavy that their masses are close to the grand unified theory scale, around 10 to the 15th power times the mass of a proton. Now here is the key. Because a right chiral neutrino has no electric charge, no color charge, and does not interact through the weak force, there is nothing in the standard model that prevents it from having an additional type of mass. A type of mass that charged particles cannot have. This is called a Majorana mass. A Majorana mass is a mass term in the equations that treats the particle and its antiparticle as the same entity. Charged particles cannot have Majorana masses because a Majorana mass would violate electric charge conservation. You cannot treat an electron as the same thing as a positron because one has charge -1 and the other has charge +1. The charges are different. Conservation of charge forbids it. But a right chiral neutrino has 0 charge. There is no charge conservation to violate. A Majorana mass is allowed. If the right chiral neutrino has a very large Majorana mass, something wonderful happens to the mathematics. The interplay between the ordinary Dirac mass, generated by the Higgs mechanism, and the very large Majorana mass, which is intrinsic to the right chiral neutrino itself, produces a seesaw effect. The physical neutrino that we observe, the light left-handed particle that interacts through the weak force, ends up with a mass that is given roughly by the square of the Dirac mass divided by the large Majorana mass. This is an inverse relationship. When one mass goes up, the other goes down. The heavier the right chiral neutrino, the lighter the observed neutrino. It is like a playground seesaw. When one side goes up, the other side goes down. And the effect is dramatic. If the Dirac mass is comparable to the mass of the heavier known particles, say a few 100 billion electron volts, and the Majorana mass is around 10 to the 24th electron volts, near the grand unified theory scale, then the mass of the observed neutrino comes out to be roughly a fraction of an electron volt. Exactly the range that experiments suggest. The beauty of this is that you do not need to fine-tune anything. You do not need to choose an absurdly small coupling constant by hand and hope that nature agrees with your choice. Instead, the smallness of the neutrino mass arises naturally, inevitably, from the combination of two reasonable mass scales. The Dirac mass is ordinary, comparable to other particle masses. The Majorana mass is large, but not unreasonably so, comparable to the energy scale where the forces of the standard model are expected to unify. And the ratio of their squares gives you the tiny neutrino mass. It emerges from the structure of the theory itself, not from arbitrary choices. This is why so many physicists find the Majorana option compelling. It does not just say that the neutrino is its own antiparticle. It explains why neutrino masses are so unimaginably small. It connects the neutrino mass to the physics of grand unification, to energy scales far beyond what any particle accelerator can directly probe. And it does all of this with a single mechanism that follows naturally from the mathematics, without contortions or special pleading. But there is a cost. The seesaw mechanism requires the existence of those very heavy right chiral neutrinos with large Majorana masses. These particles, if they exist, would be far too heavy to produce in any current or planned accelerator. Their masses would be roughly 1 trillion times higher than the energies accessible at the Large Hadron Collider. We cannot produce them. We cannot detect them directly. We can only infer their existence indirectly, through the smallness of the neutrino masses they produce, through the seesaw mechanism, and through other consequences that we will explore shortly. And the seesaw mechanism has another profound implication. If the right chiral neutrinos have Majorana masses, then lepton number is not conserved. A Majorana mass term in the equations explicitly violates lepton number by 2 units. This means that if the seesaw mechanism is real, then there must exist processes in nature where lepton number changes. Processes where the total lepton number before a reaction is different from the total lepton number after the reaction. Processes that the Dirac picture says are absolutely forbidden. This is the crux of the matter. The entire question of whether the neutrino is a Dirac particle or a Majorana particle ultimately comes down to a question about lepton number. Is lepton number an exact, unbreakable symmetry of nature? Or is it only an approximate symmetry that can be violated under extreme circumstances? If lepton number is exact, neutrinos are Dirac particles. They have distinct antiparticles. The neutrino and the antineutrino are genuinely different, separated by an unbreakable conservation law. If lepton number is approximate, neutrinos are Majorana particles. They are their own antiparticles. The apparent distinction between neutrino and antineutrino is a low-energy illusion, a practical shorthand that works in everyday experiments, but does not reflect the deeper truth. And this brings us to a question that may seem surprising. If both options are consistent with all existing data, if no experiment has yet been able to tell the difference, then why do many theoretical physicists lean toward the Majorana option? The answer is not evidence. It is aesthetics and economy. In physics, there is a long tradition of favoring explanations that explain more with less. The Majorana option, through the seesaw mechanism, explains the extreme smallness of neutrino masses. The Dirac option does not. The Majorana option connects neutrino physics to grand unification, one of the deepest goals of theoretical physics. The Dirac option does not. The Majorana option predicts specific experimental consequences we will examine in detail, that the Dirac option does not. In other words, the Majorana option is more testable. It makes stronger predictions. It says more about the world. But aesthetics and economy are not evidence. Nature does not care what physicists find elegant. The universe might very well choose the less tidy option, the one that requires an inexplicably small coupling constant, the one that does not connect to grand unification, the one that keeps lepton number perfectly conserved for no apparent reason. Physics has been surprised before by nature choosing the less elegant path. This is why the question remains genuinely, stubbornly open. Theoretical arguments lean one way, but theoretical arguments without experimental confirmation are just educated guesses. And the experimental confirmation has not yet arrived. It is worth pausing here to appreciate just how unusual this situation is in modern physics. For most particles, the question of whether they have distinct antiparticles was settled almost immediately after their discovery. The electron and positron were recognized as distinct particles within 4 years of the positron's detection. The proton and antiproton, the neutron and antineutron, all were quickly confirmed to be separate entities with opposite quantum numbers. The distinction was obvious, measurable, and unambiguous. For the neutrino, this most basic question has been open for nearly 9 decades. Majorana published his paper in 1937. It is now 2026. In all that time, with all the extraordinary advances in experimental physics, with detectors that can track individual neutrino interactions, with accelerators that can produce billions of neutrinos on demand, with observatories that can capture neutrinos from exploding stars halfway across the visible universe, we still do not know whether the neutrino is its own antiparticle. The reason is simple and humbling. The difference between a Dirac neutrino and a Majorana neutrino is invisible in ordinary interactions. When a neutrino interacts through the weak force, it behaves identically in both pictures. The weak force sees only the left chiral component. It does not care whether the right chiral partner is a separate particle or the same particle in a different state. The Dirac neutrino and the Majorana neutrino produce exactly the same electrons, exactly the same positrons, exactly the same scattering patterns in every ordinary weak interaction. You cannot tell them apart by watching them interact normally. To distinguish them, you need to find a process that can only happen if the neutrino is Majorana. A process that is absolutely forbidden if neutrinos are Dirac particles, but allowed if they are Majorana particles. A process that violates lepton number. Such a process exists, at least in theory. It is called neutrinoless double beta decay, and it is the single most important experiment in neutrino physics today. If it is ever observed, it would prove beyond any doubt that the neutrino is a Majorana particle. It would prove that lepton number is not conserved. It would confirm the seesaw mechanism as the origin of neutrino mass. And it would open the door to understanding one of the deepest mysteries in all of science. But observing it is extraordinarily difficult. The process, if it happens at all, is fantastically rare. So rare that it might occur less than once per trillion years for a single atom. To have any hope of seeing it, you need enormous quantities of material, detectors of exquisite sensitivity, and patience measured in decades. The search is underway right now, in laboratories buried deep underground in mountain tunnels and mine shafts around the world. The detectors are among the most sensitive instruments ever built by human hands. They sit in silence, shielded from cosmic rays by thousands of feet of rock, waiting for a signal so faint it borders on the impossible. What exactly they are looking for, how the experiment works, and why it is so extraordinarily difficult, these are questions we need to examine in careful detail, because the answer to whether the neutrino is its own antiparticle may well come not from theory, not from mathematical elegance, not from arguments about economy or beauty, but from a handful of atoms decaying in a way that has never been observed in the history of science. A decay so rare and so quiet that the entire universe might pass through its current age many times over before a single atom in your body undergoes it. And yet, if it happens, if even one such decay is cleanly observed and confirmed, it will rewrite the rules of particle physics and change our understanding of why the universe is made of matter rather than empty light. If the neutrino truly is its own antiparticle, then somewhere in the universe, right now, there should be atoms undergoing a type of radioactive decay that has never been observed in the history of experimental physics. A decay so rare, so improbable, so breathtakingly faint that detecting it requires some of the most extreme and ambitious experiments human beings have ever attempted. This hypothetical process is called neutrinoless double beta decay, and finding it, or failing to find it, may be the only way to settle the deepest question about the neutrino once and for all. But to understand what neutrinoless double beta decay is, and why it matters so profoundly, we first need to understand ordinary beta decay. Because the extraordinary version of this process only makes sense once you understand the ordinary version in precise detail. Beta decay is one of the most common forms of radioactive decay in nature. It happens constantly, everywhere, all around you. It is happening right now in trace amounts of radioactive material in the soil beneath your feet, in the concrete walls of buildings, in the potassium inside your own body. At its simplest, beta decay is the process by which a neutron inside an atomic nucleus transforms into a proton. The neutron does not simply vanish and get replaced by a proton. It undergoes a genuine transformation, mediated by the weak nuclear force, the same force responsible for virtually all neutrino interactions. When a neutron decays, it emits two particles. One is an electron, the other is an electron antineutrino. The neutron, which is electrically neutral, becomes a positively charged proton. The negatively charged electron carries away some of the energy released by the transformation, and the antineutrino, carrying no charge and interacting with almost nothing, flies away at nearly the speed of light, passing through the walls of the detector, through the rock surrounding the laboratory, through the entire Earth if necessary, without touching a single atom along the way. This process is well understood. It has been studied extensively for over 90 years. The mathematics describing it is precise and confirmed by countless experiments. And critically, beta decay conserves lepton number. Before the decay, the lepton number is 0. The neutron is not a lepton. After the decay, the electron contributes lepton number +1, and the antineutrino contributes lepton number -1. The total lepton number after the decay is still 0. Everything balances perfectly. Lepton number is conserved, just as it should be. Now, there are certain atomic nuclei that cannot undergo ordinary single beta decay because of the way nuclear energy levels work. The nucleus they would decay into has a higher energy than a neighboring nucleus 2 steps away. In these special cases, something remarkable can happen. Two neutrons inside the nucleus can undergo beta decay simultaneously, at the same time. Two neutrons transform into two protons, emitting 2 electrons and 2 antineutrinos. This process is called two-neutrino double beta decay, and it is an observed, confirmed, experimentally verified phenomenon. Two-neutrino double beta decay is extraordinarily rare. It is the slowest nuclear process ever directly measured. The half-lives involved are staggering. For some isotopes, the half-life of two-neutrino double beta decay exceeds 10 to the 21st power years. That is 1 billion trillion years. The current age of the universe is only about 13.8 billion years, roughly 10 to the 10th power years. So the half-life of two-neutrino double beta decay is more than 100 billion times the age of the universe. For a single atom, the probability of undergoing this decay in any given year is vanishingly small. But if you have an enormous number of atoms, trillions upon trillions of them, a few will decay even within a human lifetime. And that is exactly how experiments detect it. They gather enormous quantities of the right isotope and watch for the rare decays. Several isotopes undergo two-neutrino double beta decay.
Germanium-76 decays into selenium-76. Tellurium-130 decays into xenon-130. Molybdenum-100 decays into ruthenium-100. These decays have been observed. They are real. They are confirmed. They follow all the rules. 2 neutrons become 2 protons, 2 electrons fly out, 2 antineutrinos fly out, and lepton number is conserved. 2 electrons with lepton number +1 each, and 2 antineutrinos with lepton number -1 each. +2 and -2. Total change in lepton number, 0. Now, imagine the same process, but without the antineutrinos. 2 neutrons inside a nucleus simultaneously transform into 2 protons, emitting 2 electrons, but no antineutrinos at all. Nothing else comes out. Just the 2 electrons and the transformed nucleus. This is neutrinoless double beta decay, and if it happens, it changes everything. Here is why. In ordinary double beta decay, the 2 antineutrinos carry away some of the energy released by the decay. The total energy is shared among 4 particles, the 2 electrons and the 2 antineutrinos, and each one gets a variable fraction. If you measure the energies of the 2 electrons in many different decays, you get a broad spectrum. Sometimes one electron gets more energy, sometimes less, because the antineutrinos are taking a variable share. The total energy of the 2 electrons together is always less than the full energy available from the decay, because the antineutrinos carry away the rest. But in neutrinoless double beta decay, there are no antineutrinos. Nothing else escapes the nucleus except the 2 electrons. All the energy released by the decay goes into those 2 electrons and the recoil of the nucleus itself, which is negligible because the nucleus is so much heavier. This means that if you measure the combined energy of the 2 electrons, it should equal the full energy available from the decay. Every single time. Not a broad spectrum, but a sharp, narrow peak at one specific energy value. A spike. A line. Unmistakable and unique. This is what experimenters are looking for. Not a gradual rise and fall of events across a range of energies, which would indicate ordinary 2 neutrino double beta decay, with antineutrinos carrying away variable amounts of energy. Instead, they are looking for a sharp peak at the exact energy corresponding to the full transition energy of the decay. A spike sitting on top of the smooth background. A signal that says, these 2 electrons took all the energy. Nothing else escaped. No antineutrinos were emitted. If that peak is ever observed, the implications are immediate and profound. First, it would prove that the neutrino is a Majorana particle. Here is why. Think about what is happening inside the nucleus during neutrinoless double beta decay. 2 neutrons are decaying. In ordinary beta decay, each neutron emits an electron and an antineutrino. But in the neutrinoless version, no antineutrinos escape. What happened to them? The answer, in the Majorana picture, is elegant and startling. The antineutrino emitted by the first neutron decay is absorbed by the second neutron as if it were a neutrino. The first decay emits what we would normally call an antineutrino, a right-handed neutral particle. But if the neutrino is its own antiparticle, then this right-handed antineutrino is the same thing as a right-handed neutrino. And because the neutrino has mass, it can convert from a right-handed state to a left-handed state. If the neutrino were massless, this conversion would be impossible. A massless particle is locked permanently into a single helicity state. It cannot flip. The virtual exchange between the 2 decaying neutrons would be forbidden, and no neutrinoless signal would ever appear, even if the neutrino were its own antiparticle. Mass is what makes the process possible. A left-handed neutrino is exactly what the second neutron needs to absorb in order to undergo its own beta decay in reverse, converting the incoming neutrino into an outgoing electron. The antineutrino from the first decay becomes the neutrino absorbed by the second decay. It serves as both. It plays both roles. This is only possible if the neutrino and the antineutrino are the same particle. If they are truly different particles, as in the Dirac picture, then the antineutrino emitted by the first decay cannot be absorbed as a neutrino by the second. The process is forbidden. The two neutrons must each emit their own antineutrino, and both antineutrinos escape. You get ordinary two-neutrino double beta decay. The neutrinoless version cannot happen, so the observation of neutrinoless double beta decay would immediately tell us that the neutrino is a Majorana particle. The very existence of the process requires the neutrino to be its own antiparticle. There is no way around this conclusion. It is not a matter of interpretation or alternative models. If the process occurs, the neutrino is Majorana. The logic is airtight. Second, neutrinoless double beta decay violates lepton number. In ordinary double beta decay, two electrons with lepton number +1 each are produced, along with two antineutrinos with lepton number -1 each. The total change in lepton number is 0. Lepton number is conserved. In neutrinoless double beta decay, two electrons are produced and nothing else with lepton number escapes. The total lepton number changes by 2 units. 2 units of lepton number are created from nothing. Lepton number is violated. This would be a historic result. Lepton number conservation has been assumed to be exact for decades. Every experiment ever performed has been consistent with it. No violation has ever been observed in any process, in any laboratory, at any energy. If neutrinoless double beta decay is detected, it would be the first confirmed violation of lepton number in the history of physics. It would tell us that lepton number is not a fundamental symmetry of nature. It is only approximate. And that approximation, as we will see, has staggering consequences for our understanding of why the universe is made of matter. Now, the obvious question: why has no one observed this process yet? If Majorana neutrinos are real, why has the signal not appeared? The answer is that the process, if it exists at all, is spectacularly rare. Even rarer than ordinary two-neutrino double beta decay, which is already the rarest directly observed nuclear process. The rate of neutrinoless double beta decay depends on the mass of the neutrino. Specifically, it depends on a quantity called the effective Majorana mass, a weighted combination of the neutrino mass values and the mixing parameters that describe how the 3 known types of neutrinos relate to each other. The smaller this effective mass, the slower the decay rate, and the harder the process is to detect. Current experimental limits have pushed the half-life of neutrinoless double beta decay beyond 10 to the 26th power years for several isotopes. That is, 100 million trillion years. To put this in perspective, the universe is only about 10 to the 10th power years old. The half-life we are talking about is more than 10 to the 16th power, 10 million billion times longer than the current age of the universe. We are looking for a process so slow that if you watched a single atom for the entire history of the universe, from the Big Bang until now, the probability of seeing it decay through this specific channel would be essentially 0. This is why the experiments require such enormous quantities of material. If the probability of any single atom decaying is incredibly tiny, you compensate by watching an incredibly large number of atoms simultaneously. A kilogram of xenon-136 contains roughly 4.4 times 10 to the 24th power atoms of that isotope. If the half-life of neutrinoless double beta decay is 10 to the 26th power years, then in 1 year of observation, you would expect roughly a few dozen decays
in 1,000 kilograms of material. Perhaps fewer, perhaps just a handful. Perhaps, if the effective Majorana mass is very small, none at all, within the sensitivity of current detectors. And this is where the experimental challenge becomes almost impossibly difficult. You are not just looking for a rare event. You are looking for a rare event buried under a mountain of background noise. Every material on Earth contains trace amounts of natural radioactivity. Uranium, thorium, potassium, and their decay products are present in virtually every substance, in the rock surrounding the laboratory, in the concrete of the walls, in the steel of the detector vessel, in the wires, in the electronics, even in the bodies of the scientists themselves. These radioactive decays produce electrons and gamma rays that can mimic the signal of neutrinoless double beta decay. A gamma ray with roughly the right energy could interact inside the detector and deposit energy that looks, to the electronics, like the sharp peak you are searching for. Cosmic rays are another source of background. High-energy particles from space constantly bombard Earth's surface, producing showers of secondary particles that penetrate deep into the ground. These secondary particles can reach detectors and create false signals. This is why the experiments are conducted deep underground. The rock above the laboratory acts as a shield, absorbing most of the cosmic ray secondaries before they reach the detector. The deeper the laboratory, the better the shielding. Some of the world's leading neutrinoless double beta decay experiments are located in laboratories buried under more than a kilometre of solid rock. The Gran Sasso National Laboratory in Italy sits beneath approximately 1,400 metres of mountain. The Sudbury Laboratory in Canada is 2 kilometres underground in an active mine. The Sanford Underground Research Facility in South Dakota, housed in a former gold mine, provides nearly 1,500 metres of rock overburden. Even with all this shielding, background events persist. The rock itself contains radioactive isotopes. The detector materials, no matter how carefully purified, retain trace contamination. Radon gas, a naturally occurring radioactive element, seeps out of rock and can infiltrate the detector if the shielding is imperfect. The experiments must control every source of background with extraordinary precision. They use the purest materials available on Earth. The copper used in some detectors is electroformed underground to avoid cosmic ray activation. The LED shielding in some experiments uses ancient LED, recovered from Roman shipwrecks that sank 2,000 years ago. This ancient LED has had millennia for its radioactive contaminants to decay away, making it far less radioactive than freshly mined LED. Using 2,000-year-old Roman LED to shield a 21st century particle physics experiment is one of the more remarkable intersections of archaeology and fundamental science. Let us look at the actual experiments currently searching for this process. Several different groups around the world are using different isotopes and different detection techniques, each with its own strengths and limitations. The CAM-LAND-XEN experiment in Japan uses xenon-136 dissolved in liquid scintillator, a special liquid that produces flashes of light when a charged particle passes through it. The detector contains several hundred kilograms of xenon-136 suspended inside a large balloon at the center of the CAM-LAND detector. When a double beta decay occurs, the two electrons deposit their energy in the scintillator, producing a flash of light that is detected by thousands of photomultiplier tubes, extremely sensitive light detectors lining the walls of the detector. CAM-LAND-XEN has set some of the strongest limits on the half-life of neutrinoless double beta decay, pushing it beyond 10 to the 26th power years for xenon-136. This corresponds to an upper limit on the effective Majorana mass of roughly 60 to 160 milli-electron volts, depending on the nuclear physics calculations used to interpret the result. The Gerda experiment, which has now evolved into its successor called Legend, uses germanium-76. This experiment takes a fundamentally different approach. Instead of dissolving the isotope in a liquid, Gerda and Legend use detectors made of the isotope itself. High-purity germanium crystals enriched in germanium-76 serve as both the source of the decay and the detector that measures it. When a decay occurs inside the crystal, the electrons deposit their energy directly in the germanium, producing an electrical signal that is measured with extraordinary precision. Germanium detectors have superb energy resolution, meaning they can distinguish very precisely between events at slightly different energies. This is crucial because the signal of neutrinoless double beta decay is a sharp peak at one specific energy, and you need to resolve that peak against the smooth background of ordinary 2-neutrino double beta decay events and other backgrounds. The Legend experiment aims to deploy 1,000 kilograms of enriched germanium-76 detectors and reach sensitivity to half-lives beyond 10 to the 28th power years. At this sensitivity, the experiment could probe effective Majorana masses as small as 10 to 20 milli-electron volts. This would cover a significant portion of the parameter space predicted by the seesaw mechanism and the known pattern of neutrino mass differences measured through oscillation experiments. The Q-Ure experiment at the Gran Sasso laboratory in Italy uses a different isotope and a different technique entirely. Q-Ure uses tellurium-130 in the form of tellurium dioxide crystals cooled to temperatures barely above absolute zero, approximately 10 millikelvins. At these extraordinarily low temperatures, the crystals become bolometers, devices that measure energy by detecting the tiny increase in temperature produced when a particle deposits energy in the crystal. When a double beta decay occurs, the two electrons heat the crystal by a minuscule amount, and that temperature change is measured by extremely sensitive thermometers attached to the crystal surface. Q-Ure operates about 1,000 crystals in a large array, totaling roughly 750 kilograms of tellurium dioxide. The successor experiment to Q-Ure is called Cupid, and it will add light detection to the temperature measurement. By measuring both the heat and the light produced by each event, Cupid will be able to distinguish between events caused by electrons, which are the signal, and events caused by alpha particles, which are a major source of background. Alpha particles deposit more energy per unit distance than electrons and produce a different ratio of heat to light. This discrimination technique dramatically reduces the background, improving sensitivity to the neutrinoless signal. The NEXO experiment is a proposed next-generation detector that would use approximately 5,000 kilograms of enriched xenon-136 in a large time projection chamber. This is a detector that tracks the paths of charged particles in 3 dimensions by drifting their ionization electrons through a large volume of liquid xenon to collection electrodes. The 3-dimensional tracking allows the experiment to reconstruct the event topology, distinguishing between the 2 electron events expected from double beta decay and the single electron events produced by most background processes. By combining excellent energy resolution with topological discrimination, NEXO aims to reach sensitivities that could probe the entire range of effective Majorana masses predicted by the so-called inverted mass ordering of neutrinos. The SNO+ experiment in Canada takes yet another approach, using tellurium-130 dissolved in liquid scintillator inside the same underground laboratory that housed the original SNO experiment. The large volume of liquid and the deep underground location provide excellent shielding and a substantial amount of source material. Each of these experiments faces the same fundamental challenge. The signal they seek, if it exists, is extraordinarily faint. A few events per year, perhaps fewer, sitting on top of a background that must be reduced to comparably low levels. The entire experimental program is an exercise in extreme control. Every component of the detector must be screened for radioactive contamination. Every material must be purified to levels that push the boundaries of industrial chemistry. Every possible source of false signals must be identified, quantified, and either eliminated or accounted for in the analysis. And here is the critical point about what the absence of a detection means. The fact that no experiment has yet observed neutrinoless double beta decay does not prove that neutrinos are not Majorana particles. This distinction is essential and often misunderstood. The non-observation sets a lower limit on the half-life of the process, which translates to an upper limit on the effective Majorana mass. It tells us that if neutrinos are Majorana particles, their effective mass must be below a certain threshold. But it does not rule out the Majorana possibility. The reason is that the rate of neutrinoless double beta decay depends on the square of the effective Majorana mass. If the mass is very small, the process becomes correspondingly slower with a longer half-life. Current experiments have probed effective masses down to roughly the 50 to 100 milli-electron-volt range. But the actual neutrino masses could be much smaller than this. The lightest neutrino might have a mass of only a few milli-electron-volts, or even less. In certain configurations of the neutrino mass spectrum, the effective Majorana mass could be as small as 1 or 2 milli-electron-volts, which would push the half-life to values that no current experiment can reach. To probe these smaller masses, you need bigger detectors, lower backgrounds, and longer observation times. This is exactly what the next generation of experiments is designed to do.
Legend, with its 1,000 kilograms of germanium, NEXO, with its 5,000 kilograms of xenon, Cupid, with its enhanced discrimination capabilities, these experiments will push the sensitivity down by 1 to 2 orders of magnitude, probing effective masses in the 10 to 20 milli-electron-volt range. If they still see nothing, the following generation would need to go even further. There is a scenario in which the effective Majorana mass is extremely small, perhaps vanishingly so, due to cancellations between the contributions of different neutrino mass states. In this case, even very large detectors might not see a signal. This would not disprove the Majorana hypothesis. It would simply mean that the particular experimental signature, neutrinoless double beta decay, is too faint to detect with practical technology. The neutrino could still be its own antiparticle, but the evidence would have to come from some other observation or experiment. This is one of the sobering realities of the search. It is possible that the answer will come quickly, within the next decade or two, if the effective Majorana mass is in the range currently being probed. But it is also possible that the answer will take much longer, or that neutrinoless double beta decay alone will not be sufficient to resolve the question. The universe is under no obligation to make its deepest secrets accessible to our current technology. There is also the question of nuclear physics uncertainty. The rate of neutrinoless double beta decay depends not only on the effective Majorana mass, but also on quantities called nuclear matrix elements. These describe how the neutrons and protons inside the nucleus rearrange themselves during the decay, and they are extremely difficult to calculate from first principles. The nucleus is a complicated many-body quantum system. Hundreds of protons and neutrons interact through the strong nuclear force in a dense, tightly packed environment, and calculating their collective behavior during a rare decay process pushes the limits of nuclear theory. Different theoretical groups using different computational methods get different values for these nuclear matrix elements, sometimes differing by factors of 2 or even 3. This introduces a significant uncertainty in the interpretation of experimental results. If an experiment measures a certain half-life limit, the corresponding limit on the effective Majorana mass depends on which nuclear matrix element calculation you use. A factor of 2 uncertainty in the matrix element translates to a factor of 2 uncertainty in the mass limit. Resolving this requires advances in nuclear theory, better computational methods, and experimental measurements of related nuclear processes that can constrain the calculations. Despite these challenges, the experimental program is moving forward with remarkable ambition and ingenuity. The current generation of experiments has already demonstrated that backgrounds can be controlled to extraordinary levels. They have proven that the required technologies work. They have set limits that meaningfully constrain theoretical models. And the next generation, now under construction or in advanced planning, will push into territory where the seesaw mechanism makes strong predictions about where the signal should appear. If the signal is found, the discovery will rank among the most important in the history of particle physics. It would be the first observation of a process that violates lepton number. It would confirm that the neutrino is a Majorana particle. It would validate the seesaw mechanism as the origin of neutrino mass. It would provide evidence for new physics at energy scales far beyond the reach of any particle accelerator. And it would open the door to understanding one of the most profound mysteries in all of science, a mystery we have touched on but not yet fully explored. The question of why the universe is made of matter at all, why there is something rather than nothing. That question, and the remarkable way the neutrino's identity connects to its answer, is where we are headed next. Because if the neutrino is its own antiparticle, the consequences extend far beyond particle physics. They reach into cosmology, into the history of the universe itself, into the first fractions of a second after the Big Bang, when the balance between matter and antimatter was decided. And the neutrino, that ghostly, nearly massless, almost invisible particle, may have been the one that tipped the scales. We have arrived at the question that gives this entire mystery its weight. If the neutrino is its own antiparticle, if lepton number is not a sacred law of nature, but only an approximation, what does that mean for our understanding of the universe? Not just for particle physics, not just for the standard model, but for the deepest question we can ask about existence itself. Why is there something rather than nothing? This question sounds philosophical. It sounds like the kind of thing you might discuss late at night in a college dormitory. Interesting, but ultimately unanswerable. But it is not unanswerable. It is a precise scientific question with measurable consequences. And the neutrino, that ghostly particle we have been following through this entire journey, may be at the center of the answer. Here is the problem. When the universe began in the Big Bang, roughly 13.8 billion years ago, the conditions were extraordinarily hot and extraordinarily dense. In the first fractions of a second, temperatures were so high that particles and antiparticles were being created constantly from pure energy. Photons colliding with enough force would spontaneously produce particle-antiparticle pairs, electrons and positrons, quarks and antiquarks, neutrinos and antineutrinos. Every type of matter and its antimatter counterpart, produced in equal quantities in perfect balance. The universe was a seething cauldron of creation and annihilation, with particles and antiparticles appearing and disappearing in an endless, violent dance. And here is the critical part. In every known process that creates matter, the same amount of antimatter is created alongside it. This is not a guideline or a tendency. It is a consequence of the most fundamental symmetries in physics. Every equation that describes particle creation produces matter and antimatter in exactly equal amounts. If the universe began with these symmetric processes, and if those processes were the only ones at work, then the universe should contain exactly equal amounts of matter and antimatter today. But it does not even close. Look around you. Everything you see is made of matter. The Earth, the Sun, the stars, the galaxies. Every observation we have ever made of the visible universe, from nearby planets to the most distant galaxies 13 billion light-years away, shows matter, not antimatter. If large regions of the universe were made of antimatter, we would see the telltale signature of matter-antimatter annihilation at the boundaries. Intense gamma-ray emission from the zones where matter and antimatter meet and destroy each other. We do not see this. The universe is overwhelmingly, almost exclusively, made of matter. And yet, the Big Bang should have produced equal amounts of both. So where did all the antimatter go? Why is there an imbalance? Why did matter win? This is called the matter-antimatter asymmetry problem, sometimes called baryogenesis, when referring specifically to the excess of baryons, the protons and neutrons that make up ordinary matter. It is one of the great unsolved problems in physics and cosmology. Something happened in the very early universe, in the first fractions of a second after the Big Bang, that tipped the balance. Some process, some mechanism, produced a tiny excess of matter over antimatter, and when the universe cooled enough that particle-antiparticle pairs stopped being created and the remaining pairs annihilated each other, that tiny excess was all that survived. The overwhelming majority of matter and antimatter destroyed each other, converting back into radiation. Only the tiny surplus of matter remained, and that surplus is everything you see today. Every atom in your body, every star in the sky, every galaxy in the observable universe. All of it is the leftover residue of a nearly perfect, but not quite perfect, cancellation between matter and antimatter in the earliest moments of the cosmos. How tiny was this excess? Astonishingly tiny. For roughly every billion antimatter particles, there were approximately 1,000,000,001 matter particles. The excess was about 1 part in a billion. 1 extra matter particle for every billion matter-antimatter pairs. When the annihilation was complete, that 1 extra particle in a billion was all that remained. Everything else became photons. And those photons are still here, filling the universe as the cosmic microwave background radiation, the afterglow of the Big Bang that pervades all of space. In 1967, the Soviet physicist Andrei Sakharov identified 3 conditions that must be met for a matter-antimatter asymmetry to develop from a symmetric starting point. First, there must exist processes that violate baryon number conservation. There must be reactions in which the total number of baryons changes. Second, there must be violation of 2 symmetries, called C and CP. C symmetry says that the laws of physics should be the same if you swap every particle for its antiparticle. CP symmetry says the laws should be the same if you simultaneously swap particles for antiparticles and mirror-reflect all of space. If both C and CP are perfect symmetries, then every process that creates an excess of matter would be perfectly balanced by a mirror process that creates an equal excess of antimatter. The net result would be 0 asymmetry. To get a non-zero asymmetry, CP must be violated. Third, these baryon number violating, CP violating processes must occur out of thermal equilibrium. If the universe is in perfect thermal equilibrium, any asymmetry generated in one direction would be erased by the reverse process happening at the same rate. The universe must be out of equilibrium for the asymmetry to stick. These are called the Sakharov conditions, and they are the framework within which all proposed explanations of the matter-antimatter asymmetry must operate. The standard model of particle physics actually satisfies all 3 conditions to some degree. Baryon number violation occurs through subtle quantum effects called sphalerons. CP violation has been observed in the decays of certain particles called B mesons and kaons. And the expanding, cooling universe naturally falls out of thermal equilibrium. But there is a problem. The amount of CP violation observed in the standard model is far too small. It is insufficient by many orders of magnitude to produce the observed matter-antimatter asymmetry. The standard model can generate an asymmetry, but it generates one that is billions of times smaller than what we actually observe. something beyond the standard model must be responsible. Some additional source of asymmetry, some new physics not contained in our current equations, must have been at work in the early universe. This is where the neutrino enters the picture. And this is where the question of whether the neutrino is its own antiparticle connects, carefully and specifically, to the question of why matter exists. In 1986, the physicists Masataka Fukugita and Tsutomu Yanagida proposed a mechanism called leptogenesis. The idea is elegant and directly connected to the seesaw mechanism we discussed earlier.
Remember that the seesaw mechanism requires the existence of very heavy right chiral neutrinos with large Majorana masses, particles far too heavy to be produced in any existing accelerator. In the early universe, however, temperatures were high enough that these heavy particles could be created. Here is how leptogenesis works, in outline. In the very early universe, when temperatures were near the grand unified theory scale, heavy right chiral neutrinos were produced and existed as part of the hot plasma. As the universe expanded and cooled, these heavy neutrinos decayed, and because of CP violation in the neutrino sector, which is separate from and potentially much larger than the CP violation observed in quark decays, the heavy neutrinos decayed slightly asymmetrically. They produced slightly more leptons than antileptons. Not a large excess, just a tiny one, perhaps 1 part in a billion, similar to the observed matter-antimatter asymmetry. This leptonic asymmetry, this slight excess of leptons over antileptons, was then partially converted into a baryonic asymmetry, an excess of baryons over antibaryons, through the sphaleron processes mentioned earlier. Sphalerons are standard model processes that can interchange lepton number and baryon number. They conserve a combination of baryon number and lepton number, but they can convert an excess in one into an excess in the other. So a leptonic asymmetry generated by the decays of heavy Majorana neutrinos could be converted into the baryonic asymmetry we observe today. The excess of protons and neutrons over antiprotons and antineutrons, the matter that makes up everything. This is a remarkable chain of reasoning. The neutrino is its own antiparticle. Therefore, heavy Majorana neutrinos exist. Therefore, those heavy neutrinos decayed asymmetrically in the early universe. Therefore, a leptonic asymmetry was generated. Therefore, sphalerons converted part of that asymmetry into a baryonic excess. Therefore, matter survived the Great Annihilation. Therefore, you exist. Every atom of hydrogen in every glass of water you have ever drunk. Every atom of carbon in every cell of your body. Every atom of iron in your blood. All of it traces back through this chain to a tiny imbalance created by particles that vanished from the universe within its first trillionth of a second. If leptogenesis is correct, the neutrino being its own antiparticle is not an abstract curiosity. It is the reason matter survived. But we must be careful here. Leptogenesis is a theoretical framework, not an established fact. It is one of several proposed explanations for the matter-antimatter asymmetry. Other mechanisms exist that do not involve Majorana neutrinos. Electroweak baryogenesis proposes that the asymmetry was generated during the electroweak phase transition, when the Higgs field first acquired its non-zero value. Affleck-Dine baryogenesis involves scalar fields in supersymmetric theories. There are other proposals as well, each with its own assumptions and predictions. Leptogenesis is considered particularly compelling by many physicists because it connects so naturally to the seesaw mechanism and to the observed smallness of neutrino masses. It does not require entirely new and speculative ingredients. It uses the same heavy right chiral neutrinos that the seesaw mechanism already requires to explain neutrino masses. If those particles exist for one reason, explaining why neutrino masses are small, they automatically provide a mechanism for another, explaining why the universe is made of matter. Two deep mysteries potentially solved by the same physics. This economy is theoretically attractive, but theoretical attractiveness is not evidence. The connection between Majorana neutrinos and the matter-antimatter asymmetry is indirect. Confirming that neutrinos are Majorana particles would not by itself prove that leptogenesis occurred. It would establish that one of the necessary ingredients exists.
It would show that lepton number violation is possible, which is a prerequisite for leptogenesis. But the actual details of how the asymmetry was generated, the masses and couplings of the heavy neutrinos, the amount of CP violation in the neutrino sector at those extreme energies, these would remain unknown even after a positive detection of neutrinoless double beta decay. Leptogenesis would become a more plausible and better motivated scenario, but it would not become proven. This is an important distinction, and it reflects the honest state of the science. The neutrino identity question is connected to the matter-antimatter puzzle, but the connection is a pathway, not a proof. Establishing that neutrinos are Majorana particles would open the door. Walking through that door, confirming the full chain from heavy neutrino decays to the leptonic asymmetry to the baryonic excess, would require additional evidence that may be extraordinarily difficult to obtain. Let us turn now to the broader question of what the neutrino's identity tells us about mass itself. Because the origin of neutrino mass is not just a neutrino problem, it is a window into physics beyond the standard model, and it connects to some of the deepest questions about how the fundamental forces of nature relate to each other. The standard model, as originally written, predicted that neutrinos should have exactly zero mass. The discovery that they do have mass, confirmed through oscillation experiments, was the first clear, unambiguous evidence that the standard model is incomplete. Not just approximate, not just missing small details, genuinely incomplete. There are phenomena in nature that the standard model cannot describe. If neutrinos are Dirac particles, then explaining their mass requires adding right chiral neutrinos to the standard model by hand, and accepting an extremely small and unexplained coupling to the Higgs field. The standard model can accommodate this, but it does not predict it or explain it. The smallness of the coupling is simply postulated. If neutrinos are Majorana particles, the situation is radically different. Majorana masses arise from a mechanism that is fundamentally distinct from the Higgs mechanism that gives mass to all other particles. The seesaw mechanism introduces a new mass scale, the mass of the heavy right chiral neutrinos, which is far beyond the energies explored by current accelerators. This new scale points toward grand unification, the hypothesis that the three forces of the standard model, electromagnetism, the weak force, and the strong force, are all manifestations of a single unified force at extremely high energies. Grand unified theories generically predict the existence of heavy right chiral neutrinos with Majorana masses. They also predict that baryon number and lepton number are not exact symmetries. They predict proton decay, another process that has never been observed but is being actively searched for. Proton decay would mean that ordinary matter is not truly stable. The protons inside every atom in your body, the protons that have existed since the first minutes after the Big Bang, would have a finite lifetime, not a short one. Grand unified theories predict half-lives of roughly 10 to the 34th power years or longer, trillions of times the current age of the universe, but finite nonetheless. Experiments like Hyperkamiokande are designed to search for proton decay alongside their neutrino oscillation programs, watching enormous volumes of water for the telltale flash of a single proton disintegrating. Like neutrinoless double beta decay, proton decay has never been seen. Like neutrinoless double beta decay, its discovery would confirm physics far beyond the standard model. The connections are deep and interlocking. If neutrinos are Majorana particles,
It fits naturally into a grand unified picture of physics.
If they are Dirac particles, grand unification is not ruled out, but the fit is less natural, less economical, less explanatory. This is why the neutrino identity question matters so far beyond the neutrino itself. It is a test of our ideas about unification, about the deep structure of the laws of physics, about whether the complexity we see at low energies is the fragmented remnant of a simpler, more unified picture at high energies. Now let us survey the experimental landscape beyond neutrinoless double beta decay. Because while that process is the most direct probe of Majorana identity, it is not the only approach. Other experiments are attacking the neutrino mass question from different angles, and their results will help constrain or clarify the picture, regardless of what double beta decay experiments find. The Katrin experiment in Germany is designed to measure the absolute mass of the neutrino directly, without relying on any assumptions about whether neutrinos are Dirac or Majorana particles. Katrin studies the energy spectrum of electrons produced in the beta decay of tritium, a radioactive isotope of hydrogen. The idea is simple in principle, but extraordinarily demanding in practice. When a tritium atom decays, it emits an electron and an antineutrino. The total energy released is shared between them. If the neutrino has mass, then the maximum energy the electron can carry is slightly less than the total decay energy, because some energy is locked up in the neutrino's mass through the relationship E equals mc squared. By measuring the endpoint of the electron energy spectrum with extreme precision, Katrin can infer the neutrino mass. Katrin has already set an upper limit on the neutrino mass of under 500 millielectron volts, and is aiming to reach sensitivity to masses as small as 200 millielectron volts. This does not tell us whether the neutrino is Majorana or Dirac, but it constrains the absolute mass scale, which in turn constrains the predictions for neutrinoless double beta decay experiments. Every piece of information about neutrino mass narrows the range of possibilities and helps experimenters know where to look. The Ptolemy experiment is a proposed future project that aims to detect the cosmic neutrino background, the vast sea of neutrinos left over from the Big Bang that fills all of space. These relic neutrinos have incredibly low energies, having been cooled by the expansion of the universe for nearly 14 billion years. Detecting them would be a monumental achievement, and it could provide information about whether neutrinos are Dirac or Majorana particles. The reason is subtle. If neutrinos are Majorana particles, the relic neutrino background would contain twice as many detectable states as it would if neutrinos are Dirac particles, because there would be no distinction between neutrino and antineutrino states. This would show up as a difference in the capture rate on a tritium target. The experiment is decades away from fruition, if it is even feasible, but it represents an entirely different route to the same fundamental question. Neutrino oscillation experiments continue to improve. The Dune experiment, currently under construction, will shoot a beam of neutrinos from Fermilab in Illinois to detectors in South Dakota, 1,300 kilometers away. Dune will measure CP violation in neutrino oscillations with unprecedented precision. If CP violation in the neutrino sector is large, it would strengthen the case for leptogenesis as the origin of the matter-antimatter asymmetry. It would not directly tell us whether neutrinos are Majorana particles, but it would fill in a critical piece of the leptogenesis picture. Hyper-Kamiokande, the successor to Super Kamiokande in Japan, will be the largest water Cherenkov detector ever built, containing 260,000 tons of ultra-pure water. It will study neutrino oscillations from multiple sources, including atmospheric neutrinos, solar neutrinos, and neutrinos produced by accelerators. Its enormous size will allow it to accumulate neutrino interaction data at an extraordinary rate, improving measurements of the neutrino mass ordering and mixing parameters.
Understanding these parameters is essential for interpreting the results of neutrinoless double beta decay experiments, because the predicted rate of the process depends sensitively on the mass ordering. The Juno experiment in China will use 20,000 tons of liquid scintillator to study reactor neutrinos produced by nuclear power plants. Juno aims to determine the neutrino mass ordering, whether the two lighter neutrino mass states are much lighter than the third, called normal ordering, or whether the two heavier states are much heavier than the third, called inverted ordering. This question is directly relevant to neutrinoless double beta decay. In the inverted ordering scenario, the effective Majorana mass is predicted to be larger, making the process easier to detect. In the normal ordering scenario, the effective mass could be much smaller, potentially below the reach of even next-generation experiments. Determining the mass ordering would tell experimenters whether they should expect a signal soon, or whether they may need to push their sensitivity much further. Cosmological observations also constrain neutrino masses. The total mass of all three types of neutrinos affects the large-scale structure of the universe. Massive neutrinos suppress the growth of structures on small scales because they move too fast to be captured by the gravitational wells of forming galaxies. By measuring the distribution of galaxies and the cosmic microwave background with great precision, cosmologists can set upper limits on the sum of neutrino masses. Current limits from the Planck satellite and galaxy surveys constrain the sum to be less than roughly 120 milli-electron volts. Future surveys will tighten these limits further, potentially reaching sensitivities that could detect the minimum mass implied by oscillation data. If cosmological measurements determine the sum of neutrino masses precisely, it will further constrain the predictions for neutrinoless double beta decay and narrow the target for experimenters. This convergence of experimental approaches is one of the most exciting aspects of neutrino physics today. No single experiment will answer the Majorana question in isolation, but the combined results of double beta decay experiments, direct mass measurements, oscillation studies, and cosmological observations are closing in on the answer from multiple directions simultaneously. Each approach constrains different aspects of the problem. Together, they form a web of evidence that will eventually either confirm or rule out the Majorana hypothesis across a wide range of parameter space. Let us take stock of where we are. The question of whether the neutrino is its own antiparticle has been open since 1937. Nearly 9 decades of investigation have not settled it. Every experiment ever conducted is equally consistent with Dirac neutrinos and Majorana neutrinos. The difference between the two is invisible in ordinary weak interactions. It reveals itself only in extraordinarily rare processes like neutrinoless double beta decay, which no experiment has yet observed. And yet the question has never been more alive than it is right now. A new generation of experiments is coming online or in advanced planning, with sensitivity orders of magnitude beyond anything previously achieved. The theoretical motivations for Majorana neutrinos are powerful and interconnected. The seesaw mechanism explains the mysterious smallness of neutrino masses. Leptogenesis offers a pathway to understanding the matter-antimatter asymmetry. Grand unified theories predict Majorana masses as a natural consequence of their structure, and the experimental tools to test these ideas are being built right now in laboratories around the world by thousands of physicists and engineers working at the absolute frontier of what is technically possible. There is a version of the future in which, within the next 10 to 20 years, a detector buried deep underground registers a handful of events at exactly the right energy. Events in which 2 electrons emerge from a decaying nucleus carrying the full transition energy with nothing else escaping. Events that cannot be explained by any known background process. Events that, after years of painstaking verification and cross-checking, are confirmed as genuine neutrinoless double beta decay. In that future, we will know that the neutrino is its own antiparticle. We will know that lepton number is violated. We will have the first direct evidence for physics at energy scales 1 trillion times beyond the reach of any accelerator. And we will have a concrete, testable mechanism for understanding why the universe is made of matter. There is another version of the future in which the detectors run for decades and see nothing, in which the effective Majorana mass is too small, the process too rare, the signal forever beyond our reach. In that future, the question might remain open for generations, or it might be answered through entirely different means, through cosmological observations or some experimental technique we have not yet imagined. Either outcome would be profound. A positive detection would be one of the most important experimental results in the history of physics. A continued null result, while less dramatic, would also be deeply informative. It would constrain the possible range of neutrino masses and Majorana couplings. It would challenge the seesaw mechanism in its simplest form. It would force theorists to consider alternative explanations for neutrino masses and the matter-antimatter asymmetry. Science does not always give us the answers we want, but it always gives us real answers. Answers grounded in observation and measurement rather than speculation and hope. The search for the neutrino's true identity is science at its most ambitious and its most honest. We are asking a precise question about the fundamental nature of matter, and we are building the instruments to answer it, even though the answer might be decades away. Consider what hangs in the balance. The neutrino is one of the most abundant particles in the universe. Trillions of them pass through your body every second. They were produced in vast numbers in the first seconds after the Big Bang, and they fill all of space in a cosmic background that has been cooling for nearly 14 billion years. They are produced constantly by every star, including our Sun. They are produced in nuclear reactors, in the decay of radioactive elements in Earth's crust, in the violent death throes of massive stars that explode as supernovae and briefly outshine entire galaxies. And yet, despite being everywhere, despite outnumbering atoms by a factor of roughly 1 billion to 1, we do not know what the neutrino fundamentally is. We do not know whether it is a particle with a distinct antiparticle, following the same pattern as every other matter particle in the Standard Model, or whether it is something unprecedented, a particle that is its own mirror image, its own antimatter counterpart, unlike anything else in the known catalogue of matter. The answer matters. It matters for our understanding of mass, because the mechanism that gives the neutrino its mass depends on which type of particle it is. It matters for our understanding of symmetry, because the conservation of lepton number, one of the pillars on which the Standard Model rests, survives or falls depending on the answer. It matters for our understanding of cosmology, because the question of why the universe is made of matter rather than antimatter, why there is something rather than nothing, may be linked to the neutrino's identity through the chain of leptogenesis. And it matters because it reminds us of something we should never forget, that even after centuries of scientific progress, after building telescopes that can see 13 billion light-years into the past, and particle accelerators that can recreate conditions 1 trillionth of a second after the Big Bang, there are basic questions about the particles that make up reality that remain completely unanswered. Not questions about exotic speculations or distant hypotheticals. Questions about particles that are here, right now, passing through you as you listen to these words. Questions about the most common matter particles in the entire universe. The neutrino is the quietest particle in the cosmos. It barely interacts with anything. It passes through planets as though they were made of fog. It carries no charge, possesses almost no mass, and engages with the rest of the universe only through the weakest of forces. And yet,
Hidden inside this impossibly shy particle may be the key to some of the most profound questions physics has ever asked. Why do particles have mass? Why is the universe made of matter? What lies beyond the standard model? We do not know the answers yet, but we are looking. In deep underground laboratories, surrounded by ancient rock and shielded from the noise of the cosmos, the most sensitive instruments ever built are listening for a whisper from the neutrino. A whisper that would tell us whether this particle, this ghost that passes through everything, is truly something different from its antimatter twin, or whether it has been its own twin all along, hiding an extraordinary secret in plain sight for nearly a century. The search continues, and whatever the answer turns out to be, it will change how we understand the universe we live in.